So the last hypothesis test we're going to do for now, because of course as we dive deeper into Python, we'll have all the hypothesis tests for you and focus on which one to use when. But then we won't be going through the whole steps of the process. With the hypothesis test, we'll just talk about which hypothesis test to do when, and then how to run it in Python and interpret the results. So that's coming where we'll do lots of different hypothesis tests. But the last in-depth process we're going to work through right now is going to be the paired t-test. And so we want to talk about what it means to be a dependent sample before we do the paired t-test. So a dependent sample is when we have two samples where there is a dependency, a relationship between them. In an independent sample, we talked about how there's different people in each group. So it might be people in Alberta and then people in BC in the two different groups. In a dependent sample, there's a relationship between those two groups. They could be the same person, so we could do a pre and a post test. We assess something, we do a treatment, and then we do a measurement again to see if there's a difference. So it could be checking differences over time. And that is where we have the same people in both. This actually relates to the experimental design we talked about previously, which is the matched pair. So a matched pair design, an individual is selected to receive two treatments in a random order. So we're assessing them over time. Or we might match individuals based on characteristics so that as we're studying the effect of some kind of treatment, we can cover same income levels, same gender, same ethnicity. So we would have people with similar characteristics in both samples so that when one got the treatment and the other, say, got a placebo or a gold standard, we have already controlled then for some of those other variables that might be confounding or causing us difficulty in terms of seeing the impact. So this is that same thing we talked about previously with the matched pair. So when we're talking about a dependent sample, we either have the same people in both groups or we have paired people in order to eliminate any extraneous or confounding factors. Okay. How do we obtain paired or dependent samples? Well, if it's the same people in both, there's some kind of pre and post assessment. We could have litter mates of the same sex. So if we're doing testing related to animals, for example, we can take a litter and we could have one male from that litter in one group and a male in the other. Well, then they have the same genetics and background, the same family, right? So we've controlled for a number of factors related to their genetics. We do experiments in medical testing with twins, right? They grow up in the same environment. They have a lot of the same characteristics. And so then we can see if there's a difference. We've controlled for a number of factors. We can match people based on characteristics to help control for those other variabilities. So if we were to look at some of these examples, is this an independent or a dependent sample? So suppose we assign one group to receive sunscreen A and another to receive sunscreen B when we look at the amount of sun damage after a specific amount of time. So if we take a group and we simply divide them in half and one gets A and one gets B, these are independent samples if we randomly pulled from the group and they only live in sunscreen A or sunscreen B. If instead we use one group of people and apply sunscreen A to the right half side of their back and sunscreen B to the left side of their back, we could then compare the left side and the right side, in which case that one person is in both samples. They're in the sunscreen A group and they're in the sunscreen B group, in which case we have a dependent sample. So when we do have a dependent sample and want to compare averages from those two groups, we do what is called a paired t-test. A paired t-test, like all these other two sample tests, can have a null hypothesis where the average in the two groups is equal and the alternative is they are not equal. Or you can have a one-tailed test. You can specify that there's a difference between and how much the difference is although most of the tests really are about, is there a difference or not a difference, or is one average bigger than the other or smaller than the other, right? So often this symbol that you see here is often just 0 in these tests, because we're simply saying, is there a difference? And if there's a difference, what direction is that difference? A paired t-test has a test statistic. That test statistic is x bar 1 minus x bar 2 minus whatever we're assuming is that difference. So if we have a null hypothesis where mu1 minus mu2 is equal to 0 and the alternative is mu1 minus mu2 is not equal to 0, then this part of the test statistic is 0. Okay, the test statistic requires us to know the correlation and the standard deviation of the populations, and variances don't have to be equal in this test statistic. So we're knowing some kind of relationship within the population. We can calculate another test statistic if we don't know the correlation and standard deviation. So we are going to do an adjustment and not do the Z-score test and instead do a T, because again, if we knew that information about the population, we would probably know the population parameters, the means as well. So often we don't know a whole lot about the population at large, which is why we're doing this testing. So we're actually going to use this test statistic instead. Okay? It doesn't require you to know the correlation or relationship within the population. It doesn't require you to know sigma within the population. So we're using d bar divided by the standard deviation divided by the square root of n. The assumptions of this test is random sampling, normally distributed population. If we're using this particular t-test, so a pooled t, we are assuming that the variances and correlations are not known and that we have a dependent sample. If it was an independent sample, we would have done a separate variance or pooled t-test if the population variances were not known. Confidence intervals exist for this test as they do with all the other ones. They come from simply rearranging that test statistic. All right, let's take a look. So that d bar that was in the formula for the test statistic is the average distance between. So what we're going to do is we would take our groups. So here, for example, we have the Dean of the College of Business at Baylor wants to determine if the GPA of business college graduates decreased during the last semester of their senior year. A sample of 6 students is selected. Their GPAs are for the fall and the spring and their senior year. At a 0.05 significance level, can the dean conclude the GPA of graduating seniors declines during their last semester? So if you're doing the test statistic, you would find the difference between fall and spring, that difference column D, and then we would find the average D bar. That's what would go in our formula here. And then we need the standard deviation of the differences. That's this S sub D. Okay. So if we're doing the calculation by hand, we would calculate the difference between fall and spring. We would find the average difference, and we would find the standard deviation of that sample difference. Well, we're going to do this in Excel. It's already pre-built for us, and we're going to do it in Python as well. So we don't have to do this calculation by hand. But what we do need to do is identify what is the null and the alternative hypothesis. So here we think that the GPA of seniors declines during their last semester. So if you are taking U-fall and saying U-fall is greater than U-spring, then the average fall minus the average spring is greater than 0. Okay, so how are we arranging this? We're saying fall is greater than spring, that it is declining. So U-fall minus U-spring, mu-spring. The alternative then is that mu-fall minus mu-spring is less than or equal to 0. Okay, alpha. Alpha here, 0.05. Test statistic is a paired t-test. Assumptions of a paired t-test: random sampling, normally distributed population, correlation and variance in the population is not known, right? Let's go back to our list. Random sampling, normality, population variances and correlations are not known, and that we have a dependent sample. So make sure we list out all of those. All right. We have a t-distribution here. Our test is a greater than test. 0.05 over here, because we think fall is greater than spring. And we would get a t here based on alpha and degrees of freedom. So what is the decision rule? The decision rule is that we reject H naught if our test statistic is greater than our critical value or our p-value is less than alpha. So let's do this in Excel. All right. We are in Statistics 2, Student. So here we have 6 students. We have their GPAs in fall and spring. We are using the Data Analysis Tool Pack, so make sure you have that Analysis Tool Pack installed. Under the Data tab, we can see it here. And we are going to use a paired two-sample for means. Identify the variables, so fall is going to go first, based on the way we wrote the null and alternative hypothesis. And spring is going to go second. The hypothesized difference, we don't specify a difference, we just difference or not, so we're going to make that 0. Alpha here is 0.05. And we'll just make this bigger so we can see the output. All right, our t-statistic is 0.939. The test statistic is 0.939, and then we need our critical value. We are doing a one-tailed test, so we are here, and our test statistic is 0.93. Our critical value is 2.015. So if we were to write this out, this is 2.015, and the test statistic is 0.93. So we reject the null hypothesis if the test statistic is greater than the critical value. Well, the test statistic 0.93 is less than the critical value, so we fail to reject the null hypothesis. In fact, if you look at the data here, based on this tiny sample size, a lot of these people's GPAs went up for the spring semester. Okay. Now, we could instead look at p-values, so let's go back to Excel. We have a p-value here of 0.195. We compare that to an alpha of 0.05. If the p-value is less than alpha, then we reject the null hypothesis, and in this case, the p-value is bigger than alpha, so we fail to reject. It is possible that the fall and the spring GPAs are the same, or the fall is less than the spring. Okay. Or our sample size isn't big enough to detect the difference, which this sample size is super tiny. All right. If instead of wanting to do this in Excel, we want to do this in Python, we can do this in Python. Just a reminder, if you want to work with us in Python, go to drstephpowers.github.io/BIA. We're in Supplemental Materials, Hypothesis Tests. Click on the button that says Open in Colab. This opens a app in Google Docs. Make sure you're signed into your Google Drive. Make sure you save a copy to your drive. And we are also going to be using here the data set that is in Statistics 2. So make sure you go here to Statistics 2 and then click on Download. Okay, download it, dump it into your Google Drive, and then when you are in your Google Drive, import pandas as PD, numpy as NP. Then run this code here that will link your workbook to your Google Drive. This is not giving anybody else access. This is just linking your workbook to your Google Drive so that you can, as we scroll down to the very bottom to do our paired t-test, you can pull in the Excel file that is statistics 2, and particularly we're looking at sheet name student. In my case, this particular file I have dumped into a folder called appendix, which is inside another folder called BIBA handbook in my Google Drive. Change this part out depending on where you dumped your spreadsheet. Okay, oops. So then what we do is I'm going to give it a name. I'm going to call it dataset X9. We're going to use pandas to read that Excel file in. Then we're going to use the command head to take a look at what we've just imported. So X9, we want to look at the head of that data set. It gives us the first 5 rows. We can see the student number, fall, and spring. We are going to, from skippy.stats, import something called t-test-rel. This is going to give us the dependent t-test. So recall that in the previous ones, it was t-test-ind for independent. Now we're doing a t-test where they are related. And so the command is t-test_rel. Now, when you are doing a paired t-test in Python, it is expecting that it has, so you need to specify here with t-test-rel the columns. So we don't actually need all these columns, right? We don't need the student column. So we are going to have it just give us, I lost it here. Okay, give us the relationship between the variable fall, so column name is fall, from table X9, and then give us the column, the variable name spring, that's column spring from X9. And then we need to specify if it's two-tailed or one-tail. And so let's go back to our scenario here. Average for fall minus average for spring is greater than 0, so greater than. And then we go back in. And so this one, the command is greater to get that one-tailed test. So our test statistic is 0.939 and our p-value here is 0.195. Our p-value is more than our alpha. Our p-value is not less than alpha. So we failed to reject the null hypothesis. Okay, so with this one line of code and importing that, we can do our paired t-test as well. All right, 2 more for you to practice. I got 2 more data sets that you can do in Excel and in Python. So one is called marijuana and one is called twins. So let's just take a look at those scenarios here. So before and after seeing a film about marijuana, 16 participants completed a questionnaire designed to assess their attitudes toward the legalization of marijuana. Does watching the film on marijuana affect people's views on legalization? So can you create a paired t-test to test whether or not the film affects people's views? So choose a significance level and report your findings. The other example we have here is that 12 sets of identical twins are given psychological tests to determine whether the firstborn of the twins tends to be more aggressive than the secondborn. The test scores are shown below, where the higher scores indicate greater aggressiveness. Does the data provide sufficient evidence at a significance level of 0.05 to indicate that the firstborn of a pair of twins is more aggressive than the other? So create a paired t-test. So the difference between this example and the previous ones is these are actually different people in the 2 samples, but they've been matched. And they've been matched for all kinds of characteristics by having them be twins. Okay, so we can then compare those 2. Because there's one difference essentially between the twins, which is one was born first and the other second. They have the same parents, the same environment, the same diet. And so we've controlled for all those factors related to their genetics and related to how they were raised by the fact that they are twins. So again, a matched pair design, a paired t-test. So can you construct a paired t-test in Excel and in Python to determine if the firstborn of a pair of twins is more aggressive than the other?